Okay, so last time we left off, we had just done the third one here, right? I had gotten down to this point. The only thing that I do have left to do is substitute my u expression back in. So I know that u equals 1 plus x squared, so I'm going to replace each of those u's with a 1 plus x squared. I'll also simplify some of these fractions. So the 1/7 now, this whole thing would be 1 plus x squared, and then to the 7/2 power, minus this would be 4/5, right? So 4/5, and then 1 plus x squared to the 5/2 power, and then this would be a simple 2/3 u to the, so 1 plus x squared to the 3/2 power, right? Once again, I don't know what c is, so I have to leave that c in my expression. If they did give me a value for x, if they did tell me that x was 0 when y was whatever, then I could plug that in and find c. But we'll see an example or two of that as we get going here. But anyway, wrapping up that third question, hopefully nothing too tricky, but it is a process that you have to get comfortable. So again, if you have trouble with this, come find me and I'll get you some extra practice. So then I want to show you how we would integrate a function like this. Now, when you first look at it, you think maybe, and I hope that you think this, I could rewrite this as the integral of x to the -1st power dx. And then you might be thinking, well, couldn't I just do the power rule? Well, the power rule says I add 1, right? And so this would be x to the 0, but then I divide by that new power, so I divide by 0. And that's where problems arise. I'm not allowed to divide by 0, right? So I cannot, when I integrate this function, I cannot use the power rule. And because of that, this integral has a special property. Now the good news is this is on your equation sheet. You just have to know to recognize it, and you just have to know how to use it. So when you see the integral of 1 over x, it is important that you realize that the integral of 1 over x is actually just ln of the absolute value of x, and then plus your constant value. Now this one in particular is very, very important for us because we will see this a lot in the examples we look at from the AP questions. So this is definitely a property, definitely one you want to be familiar with. Again, it is on your equation sheet for you, which is nice, but it's very important that you start to recognize that, even if it wasn't on the equation sheet, just to help you kind of speed it up. So anyway, this example here is as easy as that. It is just 1 over x, the integral of 1 over x is ln of the absolute value of x plus c. So let's look at a slightly trickier example where we have to do some u substitution as well. So when you first look at this, now if the x squared plus 2 was on the top, you could just split that up and make that a separate fraction. But since it's on the bottom, that tells me that because the higher power is on the bottom, I'm probably going to have to do some type of u substitution. And so in fact I do. I have to make this my u. So u equals x squared plus 2. So then I'm going to do the derivative of both sides to figure out how du relates to dx, just like we did in part 1. Right? So the derivative of u equals 2x dx. The 2 would go away there, right? So the power rule brings the 2 out front, makes it x the first, and then it is in terms of dx, but again the 2 goes away. So if I look at what I've got now from my original integral, well, my original integral was 4x over x squared plus 2. Well, I've defined the bottom as u, right? That's what I did. I defined that whole thing as u. On top, I have 4x dx. I want 2x dx. So all I'm going to do is break the 4 into 2 times 2, and then I have my 2x dx. So now I have this and this, which I know collectively, right? Those two collectively form my du. So what I really then have is the integral of 2 du over u. Well, integration is always nice because any constants you can in fact bring out front. So the 2, I'm just going to go ahead and bring that out front. So I have the integral of du over u, which is the same thing we saw before. It's the same as the integral of, if I want to write this out as 1 over u du, it's the exact same thing, right? Mathematically there's no difference. So once I see this, it is very important we start to realize that, hey, this is just, when I do the integral there, it's just the ln of u, right? So the 2 is just hanging out front. I end up with the ln of u and then plus c. So at this point I'm almost done, except this is still in terms of u, and I do want to take that and substitute back in my original expression. So since I defined u once again as x squared plus 2, it seems like we've had a lot of those x squared plus somethings, but anyway, I get 2 ln of the absolute value of x squared plus 2, and then plus c. Okay, so that's what I end up with here. Now I don't necessarily need to simplify it any further. However, with the ln, it probably is worth noting that if you wanted to, right, you could bring that 2 in as a power. So you could actually make this ln of x squared plus 2 to the second power, and then plus c. And you'll see why I say that as we move forward and do some of our AP examples as well. But anyway, so nothing too tricky, right, on these last two here. As soon as you realize that you've got this special property to look at, sometimes you just have to realize that I do need to do some u substitution to help me get there. So again, it is very important that you guys get comfortable with this. Hopefully it's nothing too bad, but you will see in just a few more minutes that it is very important for the AP style questions that we are comfortable solving these types of problems. So the last one I want to do then before we get to the AP style questions is just a real brief one on this. Now e to the x is always nice, right? You guys have probably already seen that the derivative of e to the x is nice and easy to work with. If I give you this as my f of x and I say this is my function, what's the derivative, right? What's the f prime of that function? Well, the derivative of e to the x is just e to the 3x times the derivative of the inside, right? So the derivative of 3x is just 3. So I would multiply that by 3. So my f prime function here would be just 3 e to the 3x. So again, all I did was I kept the e to the 3x the same and then multiplied it by the derivative of whatever was up here. Well, I do the exact opposite, right, when I integrate. Because the integral is the opposite direction of the derivative, rather than multiplying by the derivative of the inside, I divide by the derivative of that power, right? So when I do e to the 3x and I integrate this, I still have my e to the 3x, but again, instead of multiplying by 3, I actually divide by 3, or I multiply by 1/3. So I have 1/3 e to the 3x, and then, as always, plus c, right? So the integral of this function, nothing too tricky, just ends up looking something like that. So anyway, the basics here of integration. Now I'm going to stop this part of the video here. For the third part of this video, I'm going to go back, and these were the AP questions from Chapter 3. So these were the AP questions from the Unit 3 review that we did before. You had done this problem, you had done A, B, C, and E, but I told you not to do Part D yet. Well, we're about to go back and do Part D. So for the third part of this video, I'm going to ask you guys to pull that back out, and then I'll make sure I have enough time, so I'm going to go ahead and stop this part of the video here.